Good afternoon, everyone. So today we have a great pleasure to invite Professor Chung-Yuan from NTU Chemistry, and Professor Mao got a PhD from University of Washington in 1975, and after a short postdoc at the University of Oregon and the Purdue University, he returned to NTU, and he is world expert chemistry and contribute to many fields. Now, from this physical chemistry to the all kinds of different fields, and now he's also associated with the biomedicine engineering from Taiwan Medical University, and he has also been received many awards, at least many types of outstanding research award from most. So today, Professor Mao will talk us about his story from doing this research. Most pioneering research have been done in Taiwan about this nano-confined water. So let's welcome Professor Mao.
Okay, I will just start. Okay. First of all, I'd like to thank Ken for the introduction. This is first time I come into this building. I'm just next door in Center Condensed Matter in chemistry. And I'm also thankful for Ken for his kind invitation, because we are friends for quite a while. Facebook friend. This is the first time I met him, actually. When he invited me, I'm very surprised. Why would the astronomers want to listen to me? So I think about it and decide to talk on water, because everybody think he know water, and also obviously water is very important. It's important in geology, in biology, practically everything on Earth. But surprisingly, you won't believe it, water is just about the least understood liquid of all liquids. It's very complex. It's a complex liquid, so-called. Many controversies involved, and also many cranks. You buy this water and you can live a long life, things like that. So I will try to cover part of my research and part of its implication. I want to talk about nano water. Water that's in very small space. Why we want to do that? I will tell you on the way. But I just want to say that nano-confined water is a tool. It's a tool that gives us exploration a large space of water's behavior in phase space. So that's an important thing. Okay, let's see what water is special about it. This slide shows you two very peculiar behavior water. Water has many peculiar abnormal so-called behavior. This is one of them. When you work on other liquid and you freeze it, the solid state, the solid of that liquid will fall to the bottom of your beaker. It's heavy. Obviously, because solid state, all the atoms and molecules are packed tighter in most of them. But water is not. You see this iceberg, you immediately see that obviously the volume of ice is bigger than liquid water. That's abnormal. Not many liquid, very few liquid has this behavior. And this bug can walk on water, okay? because surface tension. Water has a very large abnormal surface tension. So actually has some elasticity. The bug actually can dance on water a little bit. It vibrates. You can go on to talk about so many abnormal properties. There's a website lists the abnormal property of water. There's 41 of them. I just list 10 of them, and I just show you 2 of them. That's in red color. All the other, I won't read through it. Just say that it is unusual. First, water molecule is very small, very light. Molecular weight only 18. That's very, very small. It should be a gas, but it's a liquid. Okay, from the point of view of a universe, if you look at the elements in universe, the ranking of this is hydrogen, helium, and oxygen, and then so on. Obviously, helium cannot have any chemistry, so let's ignore it. So, but if you want to find a molecule in the universe that's most abundant, it should be water, because a molecule has to have atom, right? So this is a rich atom, and then you have a lot of water. Should be. Actually, you observe that in telescope. This is, I think this gigahertz, okay. Radio gigahertz spectroscopy, that's 11.1 billion light years away. You see water in that particular cloud. Actually, interstellar space, it's a lot of molecules, and water obviously is one of the richer one. And you can also see lots of organic molecules, small organic molecules, particularly hydrocarbons. Okay. So spectroscopy, you see a lot of water molecule and its reactions. On planets and in solar system, you also have a lot of water in other. You have this in Europa, in Callisto, and Ganymede. This is a schematic plot of the interior of Ganymede. You have the ice. Different phases of the ice. I will talk about that later. Ice 1, ice 3, ice 5, ice 6. And in between, there are liquid water. It's underground ocean. Actually, it's saline water, okay? That's something. And in this, what do you call it? Is a dwarf planet? I think it's dwarf planet. Ceres. People have been observing Ceres with spectral vehicle and see water below. This image shows the salty water. I will talk about this particularly later on. Ceres is close enough to sun, contains enough long-life radioactive isotopes, so it can continually generate heat, and so it can preserve liquid water subsurface for quite a long time. Okay, so let's see what water is. But before talking about water, I should talk about the interaction between water molecules first. Okay, this is H2O, and oxygen is negative charge, and hydrogen is positive charge. So this Coulombic attraction between two water molecules is very strong, pretty strong. Actually, we have a special name for it called hydrogen bond. It's more than a simple electrostatic interaction, the quantum mechanical effect. Anyway, this strong hydrogen bond make water is a liquid at room temperature. Otherwise, it should be a gas. If the interaction is just slightly weaker, it would be a gas because it's so light. And for each H2O molecule, you can have 4 hydrogen bonds point in a sort of tetrahedral fashion. So it has 4 neighbors in the ice structure. This is ice. So you have a periodic repetition of this structure consists of sort of hexagon structure with some open structure. That's why ice has bigger volume, because it's melted, the structure collapsed somewhat, collapsed to the extent it can flow. But still, most of this tetrahedral hydrogen bond is still maintains. If you must say, what's the difference between ice and water? I would say the coordination number, that is the nearest neighbor in ice is 4. But in liquid water, it's about 3.5. So most hydrogen bonds still maintained, but the structure collapsed to the extent it can flow. Okay. There are all kinds of ice. This is a phase diagram of liquid water and ice, the temperature and the pressure. This is liquid water. Okay, this is 0 degrees. So at very low pressure, 1 bar, its freezing point is 0 degrees Celsius. So below it is ice 1. But if you increase pressure, you will see ice 2, ice 3, ice 4, ice 7. Actually, there are more newly discovered. Notice that this is very hot. This is 100 degrees here. So you could have very hot ice if your pressure is high enough. Okay. This is the liquid water region. But the reason I want to show this, because I'm only talking about liquid water today, but the reason I show this diagram shows that underneath the structure of liquid water, the structure must be very complex, very, very complex. Otherwise, it won't have so many solid state structure. In most substance, when you examine its solid state, there are only about probably 2 or 3 solid states. Not many. Well, actually can freeze into 9 different ices. They have all different arrangements of structures. So liquid water is just sort of fluctuation combination of all these different structures. Okay, I want to tell you some stories starting from my graduate school. When I was a graduate student, I was working on statistical mechanics, theories, just pure theories. And I was very much attracted by the problem published by Austin Angell. The more important one is this. But I think his first paper is 73. I was searching for a PhD thesis problem at that time. And Angell and Speed measured the heat capacity of water down to low temperature. This is sub-zero because normal freezing point is 273, right? It's here. He just supercooled. That's metastable state, okay? It's a metastable state could be maintained if the water is absolutely clean. And it's defined, keep on increasing when you lower temperature. The lowest point is about minus 38, I think 38 Celsius. Also, isothermal compressibility seems to also blow up. What does that mean? That's very strange. Water is strange enough. It seems the strangeness, the abnormality is most prominent when it's very cold. When it's very cold. The theoretical reason is this. Okay, I plot schematically. This is heat capacity. Let's just look at the heat capacity. Okay, in previous slide I showed the actual data, but here I just show you it does increase indefinitely. Here is the normal melting point. Okay, freezing point. So there seems to be some kind of singularity behind it. And what's the meaning of heat capacity? Thermodynamic means the fluctuation of entropy, mean square fluctuation. Also, thermal compressibility is related to a mean square fluctuation of volume. So that means fluctuation is increasing very much. The structure becomes, you cannot just say randomly, it's fluctuating widely. Oh, that implies there's some kind of phase transition coming up. But unfortunately, Angell and Speedy, they could not go on further because why? That's the point. Freezing must occur, because in a metastable liquid, it can freeze at any nuclei. If there's no nuclei, it still freezes because homogeneous solution, liquid itself will form a nuclei itself by itself. So this is the point that it cannot go on. So that's a puzzle. And I talked to my professor, Professor Ron Lopez. So this is very interesting. Can I work on it? And let me look at the paper. He spent 2 days on paper. He came back to me and say, no, this is nonsense. Let's not work on it. He said nonsense because large heat capacity means that a large release of heat. He said there must be some freezing going on inside. So this is an artifact. It's not real. So I give up. I work on something else. But then I get to know Angell by communication. Then I met him in conference. So that's the situation back in the early 70s. And that continued until when we get into the. So let me explain what's going on, okay? This is stable water. And this is supercool water. This is the point that homogeneous nucleation must occur. And down below, that's accessible, that's glassy water. If you suddenly rapid cool water into glass, that's available. But this region is not accessible. As I say, homogeneous nucleation water will occur, will become ice. So this is so-called no man's land. And what Speedy's Angell's experiments go along this and come to here, okay? Because they work on normal pressure. And they say some big increase of fluctuation, And at that time, the hot research field in physics is a critical phenomenon. The normal critical phenomenon people know is this, the coexistence of liquid and gas. This line is the boundary between liquid and gas. And at critical point, near critical point, you have big fluctuation. If you look at it, it looks milky. it's one component liquid, but it's milky. That means the density is fluctuating very big, and the light sends different refractive index, and then you have a strong light scattering. But what we are talking about here, the solid ring, this is the liquid-solid boundary. You supercool here, but you hit the nucleation limit. And what people are scratching their head is, how come all these big fluctuations seems occurring somewhere here, before this limit, somewhere here. So the sense must be a second critical point down there. That's proposed by Eugene Stanley of Boston University. Okay, so there's a big debate at that time whether a second critical point. If this really exists, that means that coexistence of two liquids. You can imagine you hold a test tube, it's water, but it's separated into two layers. The below, the bottom one is high density water, and then top one's that's very weird. Really, we have never seen any liquid do that. It's one component, not two components. One component. We all know that one component solid can have different phase, but we don't know. Until that time, nobody can imagine that you can have two liquid water. Okay, but anyway, that's proposed by Stanley. It's so unusual, so people debate about it. The first line of research at the time is computer simulation, molecular dynamics simulation in particular. Around 2000, the computer power is not so big, but it's good enough to simulate a system big enough of water, because water is so simple molecule. They simulate. And they all look at this phenomena to see whether it exists in computer. Two groups, David Chandler of Berkeley and Pablo Devanetti. David Chandler and the Princeton group all use the same potential model. That is, they essentially work on same substance, same model, so there should be same result, but they get different result. Chandler claimed that supercool water is just like high-density water when observed around room temperature. There's no particular phase change expected, or nothing big fluctuation. But the Princeton group, Devanetti, they found that water could take a low-density form in addition to the high-density form everybody is familiar with. What happened? Talk about the big fluctuation. We just had one. Okay. The two groups, very important two groups, by the way, have different opinion, different results. Chandler is a big shot. No, he's a big professor from Berkeley. So Angell itself recorded at that time. It was a matter of people saying, who are you going to believe, Chandler or Devanetti? Chandler carried a big stick. So that was the situation when we entered the field. We entered from the experimental side. We decided this debate it's not for us. Now, when we experiment, we must somehow go down to the no man's land, that region that no people can have. At that time, I already turned to experimental side. I was doing synthetic chemistry. I was involved in making synthesis of porous material at that time. I gave up on theory that way already. And this is the so-called mesoporous material. Mesoporous silica. It's porous, and the solid part is amorphous silica. The synthesis is by template of micelles. This is surfactant micelle with the source of silica source, and the silica condense around this periodic structure of surfactants micelle. And then you burn away the organic part, and you get this part. This is PM picture. It's very periodic. The process very uniform. It can be controlled anywhere between 1.2 nanometer to 10 nanometer, depending on what kind of molecule you put into it. So that was the thing I was working on. By the way, that the invention was in the 1990s. So when I started working on it in 96, pretty early, I was one of the first few groups. So by 2000, I'm already very familiar with how to make this. Then we decide, oh, this is the TM picture. If you look sideways, it's channels, cross-section is honeycomb-like structure. So that's the material. At that time, I decided I should work on water because I know water can go into this place after you remove this water back in these H2O molecules. And indeed, they fill in very easy because this so-called hydrophilic material is elect water. And then the first thing we did was measure the absorption, how much water you can carry when you vary the humidity. This is relative humidity. At around 35% humidity, it go up. Suddenly, this is so-called capillary condensation. All the water just condenses into water. This is interfacial phenomenon. Normally, when you in this room, you see it's dry water going to rain. It's 100% humidity, right? In the microscopic region. But in nano region, it starts much earlier. At a very low humidity, it can condense. Fine, then I have a nano water. And all the water inside and outside is still undersaturated. So no water outside. Again, this is okay. Then what I did next is to measure its freezing behavior by using water in different size of holes. From 10 angstrom, that's 1 nanometer, 12, 14 nanometer, and so on, until 24. At 24, you see the freezing point is already much below 0. This is about minus 45. 140 maybe. I'm not sure. Anyway, you have the melting point shift down. This is water outside. It's microscopic water. We deliberately to put in. Then when you shrink the pore size, it keeps on going down until you hit this point. 16 angstrom pore never freeze. Never freeze. So for all the material down below, the water never freeze. Oh, I so break into no man's land. I say so I have a water that's very low temperature, but it doesn't freeze, never freeze. So that's good. And then I actually measure the change of freezing point for those that they can freeze against the inverse of diameter, and it does follow thermodynamic as well. So it's good. It's good. Then I met Sow-hsin Chen, Chen Sow-hsin. Right at that moment, was very lucky. I was very lucky. I met the right person. He's the professor of nuclear engineering of MIT. A great person. He's a great expert in neutron scattering. I talked to him about my system, the material, the water. He immediately light up and say, let's do some experiment of supercool water. Okay, that's the thing, was the beginning. So let me summarize. We have determined the equation state for supercool water down to very low temperature across the no man's land. Increase aqueous solubility of xenon and methane confined water. That's don't talk here. Its consequence of enzymatic activity is much enhanced. Enhanced activity is to topic was the research topic I won't talk today. Oh, okay. Then I come to implications. For this audience, I think the following 4 stories are important. I don't do research in this field, but I think what we found as important implication in geological science, in origin of life, and in water efficient area to get water. How do you get water resource? Okay, first topic is shale gas, fracking shale. This is very important technology. Actually, this technology transformed U.S. economy by making this energy self-sufficient. Before the year of 2010, U.S. is a net energy importer, oil and natural gas. That's why now you see so much trouble, wars in Middle East, because the United States want the oil, want the natural gas. But because this invention of fracking technique was developed since the late 1990s, the United States certainly has a large amount of natural gas. Actually, you see the shale gas production increased a lot since 2005, and projected to be a large part of other gas. This is high gas with a normal kind of natural gas, and this is COVID and other kind of this is all gas, but this is big increase. The technology is this: you build a sort of 专油井 with a long tube to send down this water, hot water, and plus some surfactants. Okay, and you put high pressure with this sort of frac the liquid, frac in this region there are oils and gas. By doing this, they can take the gas out. Okay. So why does this work? At that time, nobody knows. This engineer back, engineer solved this problem and get natural gas out. At that time, after we learned our confined water increase solubility, I think I know I made a simple. But this is some other people's community simulation. This is the year 2016. This is fracking, okay, or blue powder water and fracking. And very small area, okay, you blow up here. First thing is that this green part, all this green part, so-called kerosene, that's a mixture of gas and carbon, solid carbon, mixture of gas and solid, and a little bit of oil. So that means this carbon are porous. There's a lot of methane inside. You blow this up, you see this dark gray part is water. And this is water, okay? No, I'm sorry. This is water. The red and white is water. Dark gray is methane. It's methane, natural gas. If you look here, this group did a computer simulation of the process. By computer, they use a periodic carbon structure, just like material. This is our. Let's see rapid diffusion from this porous carbon material out to liquid water. Okay, why it can do this so fast? My explanation is because of both solubility. In here, there's very high concentration. It's because of compressibility. By the way, they have measured the pore size about 1 to 2 nanometers, just the region I was walking. But in this confined water, you have very high solubility of methane, so it can rapidly go out. Now, it's practically soluble, and so the barrier is not so high. Okay, if you're interested, you can look at the literature. This is first implication. The second implication is water problem. There's so many places in the world that this red region, which has water resources, probably spread dry in places. North Africa, the Middle East, and North China. Water crisis is all over the world, and it's keep on increasing because the increase of population is a big problem. So how do we get water from the very dry places? Look at this. This is my data. If I use a porous material, I can have liquid condense into my pore in very low humidity, 30 to 40% relative humidity. I can condense water. And in those areas, there's plenty of sunshine in the daytime. In daytime, you just use sunshine to drive out the water vapor and you collect and that's water. If you look at the daytime, the humidity, this is relative humidity. A place in Saudi Arabia, okay, it's fluctuating, of course, because day and night. During night, you have high humidity. Day is this 1 year. So you look at all of those places, it's all about 60%. So we can do it. Collect the water in night. When the humidity is high and daytime you dry out the water. So you can pull water out of thin air. I think that would be a good technology. That's the second. The third one is the one most interesting, talking about origin of life. There's so many theories of the origin of life. But I'm interested in the first step, not biology. It's chemical part. You first have to make these important chemical molecules, like amino acids. Okay? And this is so-called chemical evolution. How does it come about? Okay, in 1950, Wheeler and published this Berkeley famous paper that was based on so-called primordial soup theory. That's originally proposed by a Russian called Oparin. He proposed that in the original Earth, in the atmosphere, you have the following molecules: ammonia, water, hydrogen, and methane. And so they just put it in the bottle and excited by an electric spark, just spark it long enough, and they collect the result in liquid, condensed liquid, and then taste it. Going to home, they find all kinds of organic molecules, including alcohol, and more important, amino acid. They just make amino acid out of this. Well, this is very inspiring, but this is in gas, so it's very dilute. I think that most people would not believe that out of gas you form a biological system like a cell. Yes, you just cannot find the entropy. Okay, but this is approach. So let me look at some place. I talk about cirrus. Let's look at cirrus. Okay, NASA has sent a flight look down cirrus. The measure is substance and temperature. Cirrus, the temperature is between 130 and 200 Kelvin. Please remember, I did have liquid water in my confined spaces below 200 Kelvin. Okay, so that's the first thing. The second thing is they measure the spectrum to determine what kind of material is down on the surface or the subsurface, near surface of this small planet, this dwarf planet. They found this. The assignment is this. This is an OH. OH means could be water or any alcohol or whatever. That is OH. This is ammonia. Ammonia. So we have, and this is a lot of organic molecules. Most hydrocarbons. That is compound between carbon and hydrogen. And this is carbonate. So we have CO2 there from carbon. That's very interesting. I can imagine that this kind of reaction could occur. To generate the hydrogen and the CO2, you can generate methane. Because methane is one of them inside. And from methane, you can form 2 carbon, aliphatic, 3 carbon, 4 carbon, and so on. That's all in this complicated thing. Actually, they assign all the CH2 and CH2. So it's aliphatic hydrocarbon. That would be the beginning of this chemical revolution, because people have been proposed that from this ammonia, methane, H2, then you can form a small molecule, organic molecule like formaldehyde and HCN and so on. These are proven, giving good enough catalysts. And then go on more complicated. What I'm thinking is, thinking is that since all these are gas, and the Miller and Urey has to do this in gas phase. Now I know that all these gas can be soluble in liquid water in high concentration in confined space. By the way, the surface of those solid silica surface or kind of could be good catalysts. Usually they are good catalysts because they are acidic. So all this experiment that was done Miller, I think I believe that equally you can find that in nanospace. That's good because in order to what Miller's experiment, what they didn't tell you much is that they form a lot of gums from the polymers, micromolecule, very big molecule. That's sticky gums, doesn't dissolve anything. In nanospace, you won't have it because those are much bigger than my pores. So it's simple systematic, only too small enough molecule like this. That's enrichment, a gigantic enrichment, I believe. Then, under the surface of the cirrus is good enough high pressure, just a little bit below your high pressure. You have temperature around 200 Kelvin. So there's a little water. So all this original reaction could happen. base. That's my hypothesis. I'm retired. I can no longer go in that. But I'm challenged. So this could happen in a very small space. And then it formed good enough, big enough, then release out to the subsurface ocean. In that ocean, they father to other assembly to form bigger molecules. All these are big molecules. And then start to form membranes, DNA, RNA, proteins, and then they sort of mix together. All this is embedded inside the lipid layer. And that's a primitive cell. All this happened underground ocean. The proposal. Only as complex enough, they can survive themselves, they can replicate, they go out, they want to release out. Otherwise, the primitive planet is very harsh outside. It's outside very harsh. All these molecules would not survive radiation and other things. Okay, so that's my theory. Finally, I talk about application. Methane dissolved in water is known and called methane hydrate. It's an ice-like structure. It's actually flammable ice. And on Earth, gas hydrate represents more than half of all the natural gas reserve. And they can be burned because it's methane inside. So that's a very important potential for energy future. But nowadays, we're very, very careful about global warming. Methane is a global warming gas. So this digging out process must be very, very careful. Taiwan, just outside Taiwan, near Kaohsiung area, let's go to the direction of Dongsha Qundao. On the way, about 103 kilometers away, this big reserve of methane gas, hydrates. So that's very much possible. The reserve is very big. Okay, take home message. First, water is an abnormal liquid, most abundant and not well understood. Now we understand more, but I must confess there's still some thing with the colors. Water in nanospace can be supercooled in that. Supercooled water shows coexist in a two-liquid state. Solubility of non-polar gas in combined water can be increased by more than 100-fold, and several implications for your food stuff. Thank you very much for your attention.
Thank you very much. And just take one short question. We have 1 hour of time. Is there any question? Comments? Fine.
How small do those tubes or confinement chambers have to be for water control?
It depends on how low the temperature you want to go into. If you want to never freeze, it should be less than 16 angstrom. But if you can stand just more, can be bigger, but all in nanometer range.
Okay. 看下 that sense Professor Ong